So yummy.
Wow, orange juice!
Yeah.
Do you know orange juice is one of the most popular beverages consumed around the world? It is known very rich in vitamin C and providing many health benefits.
Oh, really? But have you ever wondered how much vitamin C is determined in our orange juice?
Can we determine its concentration accurately?
The answer is yes, using an analytical method known as IODOMETRIC titration.
Today, we will determine the vitamin C content in orange juice by using iodometric titration.
Why do people always say orange juice is rich in vitamin C? Because vitamin C is an essential nutrient that our body needs.
It functions as an antioxidant and helps protect our body from harmful free radicals. Vitamin C also plays an important role in collagen synthesis, wound healing, iron absorption, and strengthening our immune system.
Since our body cannot produce vitamin C naturally, we must obtain it from food sources. Among these sources, orange juice is one of the most popular and richest sources of vitamin C.
Therefore, determine the vitamin C content in orange juice is important to evaluate its nutritional quality.
So how can we determine the concentration of vitamin C in orange juice? Let's find out in this experiment.
So, what are we trying to achieve in this experiment?
First, we want to determine the concentration of vitamin C in orange juice.
Second, we apply iodometric titration as a quantitative analytical method.
And finally, we calculate vitamin C content in the dilute and original orange sample.
So, let's see how the methods work.
So now we will talk about application of vitamin C determination. The determination of vitamin C content has many important applications in our daily life. It is widely used in food quality control to ensure that the food products contain the expected amount of nutrients. It is also important for nutritional labeling, allowing consumers to know the nutritional value of beverages or the products. Besides that, vitamin C analysis can be used to monitor nutrient degradation during storage and compare vitamin C among different fruit juices. In addition, pharmaceutical and supplement industries use this analysis to verify the amount of vitamin C present in their products.
The experimental data used in this presentation were obtained from a laboratory demonstration video entitled Determination of Vitamin C in Orange Juice Using Iodometric Titration. The video demonstrated the preparation of solutions, titration procedures, observations, calculations, and final results. All the data and calculations presented in this study are based on the experimental results obtained from this laboratory demonstration.
Now let us discuss the principle of the experiment. This experiment is based on iodometric titration, which is a type of redox titration under volumetric analysis. In this reaction, vitamin C acts as a reducing agent. It reacts with iodine and converts iodine into iodide ions, while vitamin C itself is iodized to dihydroascorbic acid. After all vitamin C has reacted, the remaining iodine is titrated using sodium disulfate solution. Therefore, the amount of iodine consumed is directly proportional to the concentration of vitamin C present in the orange juice sample.
So the chemical that we used in this experiment were sodium disulfate, potassium dichromate, iodine, potassium iodine, starch indicator, distilled water, and fresh orange juice. Meanwhile, the apparatus used include the burette, pipette, conical flask, volumetric flask, beaker, and gauze cloth.
Before carrying out the titration, several solutions needed to be prepared. First, sodium thiosulfate solution was prepared by dissolving 0.625 grams of sodium thiosulfate in distilled water and making up the volume to 250 ml. Next, potassium dichromate solution was prepared by dissolving 0.049 grams in 100 ml of distilled water. This solution acts as a primary standard during the standardization process. After that, iodine solution was prepared by dissolving 0.3 grams of iodine together with 1 gram of potassium iodide in distilled water and making up the volume to 100 ml. Potassium iodide was added to increase the solubility of iodine in water. Finally, starch indicator was prepared by mixing starch with warm water, boiling it, and allowing it to cool before use.
After preparing all the required solutions, the orange juice sample was prepared. Fresh orange was squeezed and filtered through a clean cloth to remove pulp and solid particles. Then, 10 millimeters of orange juice was transferred into a 100 milliliter volumetric flask. Distilled water was added until the calibration mark was reached, producing a tenfold diluted sample. The juice was prepared immediately before analysis to minimize the oxidation of vitamin C due to exposure to air.
Next, we move to the titration procedure. First, the borate was rinsed and filled with sodium bisulfate solution. Then, 10 millimeters of diluted orange juice and 10 millimeters of iodine solution were transferred into a conical flask. The mixture was titrated with sodium bisulfate while swirling continuously. Initially, the solution appeared brown due to the presence of iodine. As the titration proceeded, the color gradually changed to pale yellow. At this stage, several drops of starch indicator were added, causing the solution to turn dark blue-purple because of the formation of the starch-iodine complex. Finally, the titration was continued carefully until the blue-purple color disappeared completely, indicating the endpoint of the titration. The final borate reading recorded was 23.4 millimeters.
Beside the sample titration, a blind titration was also performed. In this case, only iodine solution was used without adding orange juice. The purpose of the blind titration is to determine the total amount of iodine initially present in the solution. The titration procedure was repeated using sodium thiosulfate solution, and the final burette reading obtained was 25 milliliters. By comparing the blank and sample titrations, we can determine the amount of iodine that react with vitamin C.
Okay, now let's talk about results in this experiment. Firstly, the blank titration required 25 milliliters of sodium thiosulfate. Meanwhile, the orange juice sample required 23.4 milliliters. The difference between these two values was 1.6 milliliters. This difference represents the amount of iodine consumed by vitamin C present in the orange juice sample.
Starch acts as an indicator by forming a dark blue purple complex with iodine. As sodium thiosulfate reacts with iodine, the iodine concentration gradually decreases. The endpoint is reached when all iodine has been consumed and the blue purple color disappears completely. Therefore, starch plays an important role in detecting the endpoint accurately during the titration process.
Based on the titration results, the molarity of vitamin C in the diluted orange juice was calculated as 8.16 times 10 power of negative 4 molar. The vitamin C content was found to be 143.77 milligrams per liter, which is equivalent to 143.77 ppm. After correcting for the tenfold dilution, the molarity of the original orange juice was calculated as 8.16 times 10 power of negative 3 molar. Then, the vitamin C content in the original orange juice was approximately 1.43 grams per liter.
Based on the result, the blend titration required 25 ml of sodium thiosulfate, while the orange juice sample required 23.4 ml. The difference of 1.6 ml indicates that iodine had reacted with the vitamin C in the orange juice before the titration. This agrees with the principle of IODOMETRIC titration, where a higher vitamin C content consumes more iodine, leaving less iodine to react with sodium thiosulfate. Possible sources of error include parallel error when reading the borates, difficulty in identifying the endpoint, and oxidation of vitamin C due to the exposure to air. To improve the accuracy of the experiment, the titration should be repeated, the juice should be prepared immediately before analysis, and fresh starch indicator should be used.
In conclusion, the vitamin C content in orange juice was successfully determined using iodometric titration. The dilute sample contained 143.5 mg per liter for vitamin C, while the orange juice contained approximately 1.43 g per liter. This experiment demonstrates that iodometric titration is an effective and reliable quantitative analytical method for determining vitamin C content in fruit juice. Therefore, all objectives of this experiment were successful.
In my head, glitter all over the room.